Hi, this video is about open air columns or open pipes and harmonic frequencies. So whenever you're playing instruments, some of these instruments are wind instruments where you blow air through some kind of pipe or some kind of tube and it produces some sounds. There are two different ways that sounds can be produced in this way. There's open pipes and closed pipes. This video is about open pipes, where we treat each end of the air column or the air tube, air pipe, as open-ended, so that at each end here we have a standing wave that is oscillating up and down, back and forth at maximum amplitude, also known as an antinode. So that's true for every end of this open air column. Because of that, because each end has to be an antinode and there are nodes in the middle, only certain types of standing waves will fit in these pipes because there has to be an antinode at each end. And so because of that, you can only fit these particular wavelengths or size waves inside these pipes. And so there's a pattern. You can have half a wavelength here. It goes from a crest to a trough, which is just half of a wave. So a half of a wavelength. You could also go crest to crest again. That's a full wavelength, or two halves. And then here I have three half wavelengths. We can keep going on and on all the way to infinity. And we call these different possibilities harmonics. So there are only certain harmonic frequencies or harmonic waves that fit inside of an open air column. So what are some open air columns? You should think like, I always think of a whistle, or a flute is a good example. And then also like sometimes a pipe organ can have these kinds of open pipes. Now, to write this as a kind of a mathematical relationship, which we often want to do in physics, we can say that the length of this pipe can fit any number of half wavelengths inside of it. So that's one way to write that. The length of the pipe is equal to n over 2 wavelengths, where n can be 1, 2, 3, so on. But for frequencies, it's similar to the case with a string that's fixed at both ends. Because we can fit any number of half wavelengths in here, the frequencies of each harmonic is equal to n times the speed of the waves inside the pipe divided by 2 times the length of the pipe. So this is our harmonic frequencies inside the pipe. So with that being said, let's look at a word problem involving these situations. So it says here, blowing air over the mouthpiece of a flute, standing waves form within the open-ended air column of the flute's body. Suppose the length of the air column is about 65 centimeters and the fundamental frequency of the note being played is 256 hertz. What is the wavelength of the first harmonic frequency? 2, in meters per second, what is the speed of the sound waves in the flute's air column? And 3, determine the frequency of the second harmonic. Okay, so that's a lot of things to do there, but let's just take it one step at a time. I'm going to start by drawing a picture again. And I wanted you to notice there's one particular phrase in there called the fundamental frequency. And so fundamental frequency is the frequency that is the lowest possible harmonic frequency that can fit, and it's also the one that we often hear as the loudest, or we perceive it as that particular pitch. And so that means n equals 1 for this kind of wave that we're talking about. So that means when I draw a wave here, it's going to be from one antinode to another, a crest to a trough, and vice versa. It just flips back and forth like that. So we have half of a wavelength in there. Okay, so that already kind of helps us answer the first question, which says, what is the wavelength of this wave? And we know that the length of the pipe right now is 65 centimeters. But also, the length of the pipe is also half half of a wave inside of there. So rewriting this equation right here with n equals 1, the length of the pipe is 65 centimeters, and we're dealing with half a wavelength here. So if we multiply both sides by 2, we'll find our wavelength, which is 130 centimeters. So that's our wavelength. Now we might want to write this in meters later because we're going to be solving for meters per second in number 2. So we can divide this by 100 and that gives us 1.30 meters. We only need 2 sig figs, so we'll just do 1.3 meters. Okay, so that's our wavelength for this wave. That's number 1 done. Number 2, it says, what's the speed of the sound waves in this air column? And so we're going to use that longer equation now involving the frequency, this one, because it has speed in it. And we're going to put in the things that we know about this particular wave. So we know that the fundamental frequency, it said, was 256 hertz, if we look back at the problem there. So I'll put in 256 cycles per second. N equals 1. The speed is what we're looking for. And then divided by 2 times the length of the pipe, which in this case, we're going to convert it to meters. So 0.65 meters instead of 65 centimeters. Now to solve for all of this, we can kind of start simplifying things. So we have 256 hertz over here equals 1 times v, which is just v, and then this is 1.3 meters on this side. So we're going to multiply it by 1.3 meters on each side. And that will give us an answer of 332, but I'm going to round that to 330. So 330 meters per second. This is a pretty reasonable answer because the speed of sound in air is 343 meters per second. And so it's pretty close to that value there. And then the last thing we're asked to find is determine the frequency of the second harmonic. And so we're just going to take this equation that we just did, and instead of using n equals 1, we're going to use n equals 2. So we're going to do F2 equals NV over 2L, and n equals 2 now. So F2 equals 2. And you might wonder, what's the speed here? But once you find the speed one time, you found it for every wave, because the speed of a wave only depends on the medium. So if you find the speed of the wave for one frequency, that speed is going to be consistent for every harmonic frequency because there's only one speed possible based on the properties of the medium. So we're going to use that same speed that we just found and then divide this by 2 times 0.65 meters. So now we kind of do some multiplying here. So this is going to be 660 meters per second divided by 1.3 meters. And so our frequency of the second harmonic is equal to 660 divided by 1.3, 510 rounded up there. Now I did this kind of the long way, but you might know, okay, this is just double of the original fundamental frequency over here of 256. So we did it the longhand way, but you might see the shortcut there and take the shortcut option. So anyway, that's all I've got for you in this video. Remember, the opposite of love is not hate, but apathy.